Any other questions? All right. So in the previous class, we looked at some examples of duality, strong duality, and generally looking at the dual of a given optimization problem. Right. So let's now see some cases where duality can help, and expanding on what I mentioned earlier, how do we solve convex optimization problems? Are there scenarios where we can get closed form expressions? And in what cases can we obtain such closed form expressions? And what are necessary and sufficient conditions under which the sort of method or procedure that we used will work? Right. So let's first look at the following properties. So now let's assume that for now we'll assume that f of x. So we have an optimization problem. So we want to minimize some f0 of x subject to fi of x is less than or equal to 0 to m, and hi of x equal to 0 for j equal to 1, 2, 3 up to k. And we won't make any further assumptions on the functions f0, f1, and so f0, all the fi's or the hi's. The only assumption that we will make is that there exists at least one feasible point. All right. Let's also assume that there is some x star for which f0 of x star. So this x star is feasible, which means that it satisfies all the constraints, and this f0 of x star achieves the optimum value. So this is an optimal point. Right? No further assumptions. I'm not assuming that f is convex. Right? It could be non-convex for all I care. Right? And let us suppose that g of lambda v is also, so we have a d star which is equal to the supremum for all lambda greater than or equal to 0 and v in our k. So we'll also assume that there exists a point lambda star and v star for which this d star is achieved. Okay. Any questions? So feasibility and achievability. D star is a max. Right. So let's look at any point x, not necessarily x star. So if I look at f0 of x minus p star, which is the optimum value of f0 of x subject to all the constraints, what can I say? Okay, so firstly, even before that, we know that p star is always going to be greater than or equal to g of lambda v for any lambda v which is dual feasible, or in other words, lambda is greater than or equal to 0 and v is in R. right? So this is what we call dual feasible. So what this means is that if I look at f0 of x for any point x, for any, let me say, feasible point x, if I look at f0 of x minus p star and compare this with f0 of x minus g of lambda v for any dual feasible lambda and v, then what can you say about these two quantities? Is there some relationship? So this is less than or equal to f0 of x minus g of lambda comma v, right? So if you know that f0 of x minus g of lambda comma v is small, then it means that f0 of x is pretty close to the optimum, correct? And that can sometimes be very helpful. So what this implies is that x is an epsilon approximate solution, right? So this is an an epsilon approximate or epsilon optimal, approximately optimal solution, where epsilon is equal to f0 of x minus g of lambda, right? And this holds for any point x which satisfies the constraints and lambda v which is dual feasible. So this difference f0 of x minus g of lambda v is sometimes called the duality gap. Right? And why is this particularly helpful? Let's suppose that you design some kind of an optimization algorithm, right, to solve this particular minimization problem. Okay? So let's assume that this is an iterative process. So you start with, you iteratively get an x1, x2, x3 up to xk, but you ultimately want a stopping point, right? You don't know when to stop. So for example, when you used something like gradient descent, what you could say was, if the gradient is close to 0, then you stop, right? But that is not guaranteed to give you a global optimum. All you could guarantee using such an approach was that you were somewhere close to the local, you were close to a local optimum. But that tells you nothing about whether you're even close to a global optimum, or you could be at a local optimum, but it could be very, very far away from the global minimum. But on the other hand, suppose I designed an algorithm which gives me a sequence of not just xk's, but also dual feasible points. So lambda 1 v1, lambda 2 v2, and so on up to some lambda k vk, right? So suppose we design some algorithm. It could be something like gradient descent, but it could be something different. Well, where this is primal feasible, so it satisfies the constraints of the original problem, and lambda t vt are dual feasible. Then this gives this particular statement that f0 of x minus p star is less than or equal to f0 of x minus g of lambda v gives kind of a natural way to determine a stopping point. If x f0 of xt minus g of lambda t vt is now less than or equal to epsilon, then you're guaranteed that the xt is an epsilon approximately optimal solution. Right? Even without knowing the true value of the optimum, you now know if you're epsilon close to the optimum. So f0 of x minus p star is going to be less than or equal to epsilon. So a natural stopping point for your iterative algorithm would just be to evaluate f0 of xt minus g of lambda t vt. If it is less than or equal to a particular threshold, then you stop. And you're guaranteed to be close to the global minimum. Right? Any questions? Now, of course, so far we've not, at least for this property to hold, we don't need convexity. It could be a non-convex problem. But if you want to get arbitrarily close to a solution, to the true minimum, then what you need one property, and that is strong duality. So all of this will hold only if strong duality holds. Otherwise, these two could be arbitrarily far away from each other, and you wouldn't even know if you're close or not. So you need, so the only mild condition that you require is strong duality. Right? So let's assume that we actually have strong duality, right? And basically you can achieve, there exists an x star which solves the original optimization problem, which achieves the minimum, and a lambda star v star which solves the dual problem, right? Which maximizes g of lambda comma v. Yes.
For all the so far to hold, we need strong duality.
Which one?
So far we need strong.
We don't need strong duality, but for this to be useful, you need strong duality.
Wouldn't weak duality be?
Yes, but then there may not, if weak duality, if you have only weak duality, then how do you choose your epsilon? You may never get epsilon close to the optimum value. So unless you know what the minimum duality gap is, if you know what the minimum duality gap is, then there is hope. But otherwise, if you don't even know what the duality gap is going to be, then you can't really say. But if you have strong duality, then you can choose an arbitrarily small epsilon, run your algorithm until you get epsilon close to, until the duality gap becomes less than or equal to epsilon. Right?
Most of these cases, when we need to come this arbitrarily close, that means that like for a very small value of the function, we have to have a very large gap in x, right? Otherwise, it will be easy to restore.
I'm not sure what to follow.
Okay, so for example, one case where this would be useful is if we have something like 1 by x as the function. Right?
Okay, why is that?
1 by e power x, you know, graph like that. In
Okay.
that case, this property would be useful, right? Because in all other cases, it would be easy to reach the optimum once we come arbitrarily close.
But you don't know if you're arbitrarily close, right? The point is, how do you determine whether you're arbitrarily close to P star or not? Because you don't know P star, correct? You have some iterative algorithm, you don't know the value of P star. And I mean, this of course becomes interesting when the problem is non-convex, right? If it is convex, then fine. If you can find the gradient, then if the gradient is close to 0, then you know that you're close to the optimum value. But if the function is non-convex, then the gradient may be close to zero, but you have no way of knowing whether you're close to the global minimum or not. But in case you're able to evaluate some dual feasible points, then there is hope. There's hope of determining whether you're close to the optimum value, to the global minimum or not. So I'm saying that design an iterative algorithm. If it's a bad iterative algorithm, then you may never achieve this. It's up to you to design a good iterative algorithm. But if you have an algorithm for which is sort of guaranteed to converge to the minimum eventually, then you know exactly when to stop.
You have weak duality, that means like whatever epsilon I'll get,
Yes.
that's still good. I just do not know when, like my epsilon will, like my epsilon might not converge to zero.
Exactly.
The whole epsilon formulation is still valid.
The formulation is still valid, definitely. But if you know nothing more, right? If you don't know what the minimum duality gap will be, then you don't know how to choose your epsilon. You can evaluate the duality gap. Let's say that the duality gap is 10. I don't know whether I'm really close to the optimum value or far away. But if I know that the minimum duality gap is going to be 10, then I know that I'm close to it. Any other questions? Okay. So let's suppose that strong duality holds and both problems are solvable. Right? So there exists points which achieve the minimum of the primal problem and the maximum in the dual problem. Right? So let's look at f0 of x star. Right? So this would be equal to f0. So this would be equal to the dual. So p star is equal to d star, right? So this is equal to g of lambda star p star. Right? Because again, we're just assuming that strong duality. But what is g of lambda star v star equal to? This is equal to the infimum over all possible x of f0 of x plus summation over all I lambda I f I of x plus summation over all j vi h I of x. Right? But this is less than or equal to. So this holds for the minimum of x. So if I look at evaluate this as x star, then this quantity is going to be greater than or equal to the infimum value. So this is f0 of x star plus summation I equal to 1 to m lambda I. Sorry, these should have been lambda I star and vi star. Lambda I star fi of x star plus summation j equal to 1 to k of vi star hi of x. Question? Sorry, which one? The minimum, this infimum. The infimum is over all points in the domain of f0, fi, and hi. This is not a constrained minimization problem in that sense, right?
But lambda is constrained to be.
Lambda is constrained to be greater than or equal to. I mean, it's the optimizer for G, so obviously lambda star should be dual feasible. Yeah, so in this case, yeah, it's the infimum over all possible x. F of x, f0 of x star. No, so this is the infimum over all possible x, right? And x star obviously belongs to the domain. So this function, the Lagrangian evaluated at x star, is going to be greater than or equal to this particular quantity, right? That's the only thing I used. So x star is not the one which minimizes the Lagrangian. It's the one which minimizes f0 of x subject to the constraints. The minimizer for the Lagrangian could be different from x star. That's something to keep in mind.
So for here, if I have x star has to be 0, right?
Which one? Fi of x star has to be less than or equal to 0. Well, we'll come to that later. But it's not necessarily true again.
Lambda.
Let's not jump to that yet. Just yet. Let's not jump to that yet.
That it's an optimal solution. That is why. What does this imply? Does it have any other implications? Then this is kind of obvious, right? If we know that x star is not.
It is no. I want to find out what are the properties of under which optimality holds. What are some properties of the optimal solution? Okay.
Some question, but can't tell us lambda star and v star to be
Lambda star and v star to always be 0. Why?
because then
Which equation always holds?
not x.
Yes, but that may not be the infimum or all possible x, right? So x star is the one which achieves the constrained minimum of f0 of x, right? So just to recall, so x0 star equal to the minimum of f0 of x. It's not the minimum of L of x lambda v, subject to the constraints that fi of x is less than or equal to 0 for all I and hi of x equal to 0 for all I. But on the other hand, this minimization problem does not have these constraints, right? This is a completely different function. I mean, it's a class of functions, one for each value of lambda and v, right? Each lambda and v gives you a different function, and you're looking at the global minimum of that particular function. So this and this need not be the same. In general, they will not be the same. Right? Any questions? Okay, but I have an f0 of x star on the left hand side and an f0 of x star on the right hand side. So this means that zero is less than or equal to summation over all I lambda I star fi of x star plus summation j equal to 1 to k vi star hj of x star. So we know that lambda star is obviously dual feasible. V star is in R and X star is primal feasible. Because after all, it solves the original primal problem, right? So what can you say about this quantity? Summation j equal to 1 to k, 1 to k, vi star hj of x star. This should be equal to 0, right? Just because since x star is primal feasible, hj of x star, it should satisfy all the constraints. So hj of x star should be equal to 0 for all j. Okay, so this implies that this summation should be equal to 0. Correct? But what do we know about fi of x star? Less than or equal to 0. Lambda I star greater than or equal to 0. So when can this summation be equal to 0? When each lambda I star fi of x star should be equal to 0. Right? No such property holds for v star. V star could be arbitrary. But this is kind of an interesting property, right? What this says is that now, let's suppose I look at I try to find the stationary point of the Lagrangian, right? So basically, I'm trying to find the max min of the Lagrangian, and I get some particular point. So at this optimum point, it must be the case that for every I, either lambda I star equal to 0 or fi of x star equal to 0. Correct? If lambda I star is strictly greater than 0, then it must mean that the optimum value, the x star which achieves the minimum, must satisfy the constraint with equality. And that's some property that we have not seen, at least so far. So this is something new. And this is what is called complementary slackness.
Lambda I star being 0 would mean the constraint was not important at all. Yeah, that's
Not necessarily, right? The constraint is still important, right? Because no matter what happens, fi of x star should be less than or equal to 0. It can't be greater than 0. Right?
Is
What
there any significance of lambda I star?
it sort of forces so if lambda I star equal to 0, then potentially the x star which achieves this could be at kind of an interior point, that is fi of x star is strictly less than 0. But on the other hand, suppose that all the inequality constraints, the optimizer achieves is one such that all inequality constraints are satisfied with equality, then it sort of forces each lambda I star to be equal to so each lambda I star could potentially be greater than 0. That's the only point that I'm trying to make. Okay. So these are sort of necessary conditions, right? I'm not in any sense saying that these are sufficient for a point to be optimal. So let's maybe list out all the points, all the properties that an optimum set of points should satisfy. Let's also maybe assume that uh, the all the functions that we have are differentiable. Right? Okay. So obviously the optimum value. Okay. So suppose that all the fi and hi are differentiable. Then clearly the first point is that the x star should obviously satisfy all the constraints. So the first thing that we have to have is that fi of x star should be less than or equal to 0 for all I. Hj of x star equal to 0 for all j. The third property is that the lambda I star should be greater than or equal to 0 for all I. Just because x star and lambda star are feasible. And a new property that we have is that lambda I star fi star of x should be equal to 0 for all I. Right? So those are properties that we have so far. Now we see one more property that a differentiable problem should necessarily solve. So let's look at x star. In fact, L of x star lambda star v star. Right? What is this equal to? This is f0 of x star plus, is there anything else that remains? Correct. So it's summation I equal to 1 to m1 to m lambda I star fi of x star. But what is that equal to? It is 0, right? I have at this, so I'm looking at this particular point, the optimum point, right? So I know that lambda I star fi of x star should be equal to 0. Each hj of x star should also be equal to 0, which means that f0 of x star, so the Lagrangian is equal to f0 of x star. Nothing new here. But let me now take any point L of x lambda star v star for any feasible point x. This is now equal to f0 of x plus summation I equal to 1 to m lambda I star fi of x. Anything else? That's it, right? Because since x is feasible, each hj of x should be equal to 0, right? But what can you say about this particular quantity? This should be less than or equal to 0. Right? but now if I compare f0 of x star with, or L of x star lambda star v star with L of x lambda star v star, can I say something? Yeah. And why is that?
Plus that part is
Okay. So you're claiming that if, so okay, what I want is, what can I say about L of x star lambda star v star compared to L of x lambda star v star? Less than or equal to, and why is that the case? You're right, this is indeed true, but there's a special reason why this is the case. I mean, it's not evident from this property.
That would be the infimum of, that is basically G of
Correct. So this L of x star lambda star v star is basically G of lambda star v star, right? Because this is equal to f0 of x star, right? But this G of lambda star v star equal to the infimum overall possible x of L of x lambda star v star, right? So x star in fact achieves the minimum of the Lagrangian, but only for a special case, when you choose lambda equal to lambda star and v equal to v star. Otherwise, you can't say that x star also minimizes L of x lambda v.
So f naught of x would go positive in a rate higher than lambda star.
Yes. That x is achieved at x star. Correct. Well, I know that L of x star lambda star v star equal to G of v star lambda star v star. You agree with that, right? Correct. But we know that its strong duality holds. So this is equal to f0 of x star. Right? So x star solves the original primal problem. So f0 of x star equal to this, but this is equal to the infimum. But this f0 of x star is also equal to L of x star lambda star v star, right? Just because of this. So L of x star lambda star v star equal to g of lambda star v star, which is equal to the infimum. So x star achieves the infimum. So in fact, this is the minimum overall possible. Okay, so this means that x star minimizes L of x lambda star v star. So if I take the gradient with respect to x, gradient of the Lagrangian with respect to x, that should be equal to 0, assuming that the problem is differentiable. So this implies that the gradient f of, let me just write it above. That's another property that we have, that the gradient of the Lagrangian evaluated at lambda star x star lambda star v star, the gradient taken with respect to x, which is gradient f0 of x star plus summation over I lambda I star f gradient fi of x star plus summation over all j vi vj star gradient hj of x star should be equal to 0. Right, so we have a set of necessary conditions for x star lambda star v star to be optimal, right? Primal dual optimal. So these are what are called KKT conditions. Named after Karush, Kun, Tucker. And these give necessary conditions for a point to be optimal. So this gives us sort of a recipe for solving a convex optimization problem. Again, it's not very easy, but suppose we want to solve the given constraint optimization problem. The solution effectively boils down to solving a system of equations. We originally started out with a problem of minimizing a particular function subject to constraints. Now we've reduced it to finding x star lambda star v star, which satisfy these inequality and equality constraints. Right, so from a minimization problem, effectively we've come down to a feasibility problem. Find some point which satisfies these conditions. But of course, these are necessary conditions. But as it turns out, if your problem is also convex, then these conditions become sufficient as well. Now, one reason why, an immediate reason to see why this is not always sufficient is that ultimately what we want to find an x star lambda star v star, which basically minimizes the Lagrange, right? The Lagrange dual function. So But with the fifth condition that we have, basically just says that the gradient of the Lagrangian with respect to x is equal to 0. Right? For a given lambda star v star, L of x lambda star v star need not be convex. Correct? If, for example, if f0 is not convex, then L of x lambda star v star is not going to be convex. So just because the gradient equal to 0 does not imply that it actually minimizes the Lagrangian itself. So that's one reason why in general this is not going to be sufficient. But on the other hand, if you have a convex optimization problem, then the point that then the gradient, the point at which the gradient equal to 0 is also going to be the minimizer of. So just to see why, if x star lambda star v star satisfy KKT conditions, then so let's assume that x tilde lambda lambda star v star equal to 0 implies that x star minimizes L of x lambda star v star, and that's simply because L of x lambda star v star is going to be convex. It's a sum of convex functions, so that's going to be a convex function, right? Yeah. Sorry? That's what we're assuming. That so convex optimization problem is one wherein all the FIs are convex and all the HJs are affine. That's going to be. It could be, and potentially you could choose non-affine functions H so that the constraints still form a convex set. But for us, a standard convex optimization problem is going to be one wherein all the HJs are affine. Right? So x star will minimize this, and we know that the minimizer x star lambda star v star is equal to g of lambda star v star, but this is also equal to f0 of x star. And why is this the case? Yeah? Not yet. So I want, without using strong duality, why is g of lambda star v star? Just purely, I just want a set of points x star lambda star v star which satisfy the KKT conditions.
Because we have that lambda.
Correct. So firstly, x star minimizes L of x lambda star v star, and because of that, L of x star lambda star v star equal to g of lambda star v star. That's one point that we have, right? But what is L of x star lambda star v star going to be equal to? It's f0 of x star plus the remaining terms But according to the KKT conditions, all the remaining terms should be equal to 0. Right? So you're left with just f0 of x star. So at this particular point, we have g of lambda star v star equal to f0 of x star. But when can that happen? So basically the duality gap is equal to 0, which must mean that x star is indeed the optimum. Right? Yeah.
We had to say condition that for strong duality to hold
Correct.
even in Convex cases, we need a specific
We
condition.
need a specific case.
So if these conditions are sufficient, is that condition somewhat implicitly implicated in these conditions?
No. So okay. Is it implicitly assumed?
They
So
implicit in the KKT.
in a sense, it is going to be implicit in the KKT condition. It's not evident that that's the case, but that will happen.
Does this have any geometric implications?
Which one?
This more like the zero duality gap. Is there any geometric implications?
It's a little. What do you mean? The geometric
So
implications
for
of
example, if you have both the curves, they touch at the optimum point or something like that.
they don't touch at the optimum. That's the whole thing.
Then
So again, you can't really say that because they're problems that live in different, they're functions that live in different dimensions, right? You can of course consider problems where both of them live in the same dimension. So for example, a function of one variable involving one equality or inequality constraint. So in that case, you could sort of compare the two, but in general, you can't look at both functions in the same way.
or is there anything saying that okay, one can be a linear transform of the other things like
Not really. Okay, so any questions so far? Okay, so now we basically have a recipe for solving convex optimization problems. It doesn't mean that it makes our problem much easier, because after all, we still have to somehow be able to solve the solve for the KKT conditions. But let's begin by looking at an example. So this is a problem which comes from information theory and wireless communications, and it's the following problem. So it's a problem of maximizing the throughput or the rate subject to a certain power constraint. So it's a problem of optimal power allocation across multiple channels. Right. So again, if you've seen this problem before, then you know what I'm talking about. But even in case you've not seen the problem before, let's assume the following case where you have some kind of a power budget, okay, and you have multiple channels, multiple noisy channels over which you can transmit information. So you have channel 1. In fact, you can just assume that these are additive channels. So this is Z1, Z2, Z3, Z4, and so on. Right? There's one transmitter, one receiver, and there are multiple sort of channels over which you can transmit information. Okay, you know that the noise is Gaussian. Okay, and you know the variance of the Gaussian in each channel. So this is, let's say, sigma 1 square, sigma 2 square, sigma 3 square, sigma 4 square, and so on. You know the values of these sigma I square. And you have a total power budget. And you can transmit information, not necessarily the same information, but you can encode your messages. And with different amounts of power, you can transmit information in each of these channels. You can allocate a total power budget of P1 to the first channel, P2 to the second channel, P3 to the third channel, and P4 to the fourth channel. The goal is to ensure that the total amount of information that you're sending, the total rate at which you're sending information is as large as possible. Now, one can show that the amount of information per channel used, the rate of information that can be sent across a channel, if you have a power budget of Pi, and you have noise with variance sigma I square, the rate at which you can transmit through the ith channel is in fact half log 1 plus Pi by sigma I square. You can think of this as the throughput that you can achieve on a channel over which you can transmit at power I, and the noise variance is the noise power is sigma I square. Sorry?
What is that?
Half, sorry.
No, like,
Which one?
the diagram.
Okay, each Zi is so that's a Gaussian random variable. You can think of Zi as the noise in the ith channel. Right? So basically, I have access to, let's say, m different channels. I can transmit across all the m channels if I want, or I can select one of these channels or some subset of these channels and transmit across them. But I have a total budget of, let's say, P, right? I don't have an unlimited power constraint. This is my total budget. I can distribute this power across multiple subchannels, multiple such channels. So the overall rate at which I can transmit is summation I equal to 1 to m r. And the goal is to achieve the largest rate possible subject to a power constraint. So what does intuition tell you? What do you think you should do?
Sigma is, this one.
Okay, so let's suppose that sigma 1 square is the minimum. So sigma 1 square is strictly less than sigma 2 square, which is strictly less than sigma 3 square, and so on. So you're saying that you should just pump in all power to that particular channel.
Okay, no, it's a constraint. Probably Pi by sigma I square should be equal for something like that.
Okay. So how many of you have seen this problem before? Quick raise of hands. How many have seen this before? So the others have not. So any other guesses? What would be an optimal solution? How many of you would say that, okay, you pump in all power to the channel where the noise variance is the minimum? No one wants to go for that solution? Okay, that would have seemed so rather the most intuitive solution. Okay, so it means that you should distribute power across multiple channels instead of putting in all the power into one channel. So anyway, well, we know how to solve convex optimization problems. Let's go ahead and solve this. Right? So let's perhaps work with some simpler sort of variables. Uh, so anyway, so our goal is to maximize r equal to summation I equal to 1 to m of some constant. Let's assume that it is just log sigma I square plus pi. So this is my objective function. This is my objective function, and maximizing this is the same as maximizing r. You agree? I just take sigma I square plus pi divided by sigma I square. The sigma I squares are all constant, so I just take them. Okay, so the goal is to maximize this subject to summation I equal to 1 to m pi less than or equal to p. Let us go ahead and compute the Lagrangian. This is
also be a non.
Sorry?
There should also be a non-negativity constraint on the power.
There should be a non-negativity constraint, I agree. But what happens if the pi is smaller, is less than 0? It's a monotone function in pi anyhow. So for now, let's not worry about the non. Pi plus lambda times summation I equal to 1 m pi is less than or pi plus Alright, okay, so let's also impose the non-negativity constraint. P strictly greater than or equal to 0. So that would be pi plus, let's say, lambda 2 transpose p should be greater than or equal to 0 minus lambda 2. So I have p greater than or equal to 0 or minus p less than or equal to 0. So I have lambda times summation pi minus p. This is going to be my f1. The other function is basically equal to. Okay, let's find the gradient of L with respect to P and with respect to lambda. Or in other words, let's just evaluate the KKT conditions. So first, gradient of L of P lambda taken with respect to P should be equal to 0. So what does this imply? What is the gradient of this with respect to Pi? Or what is the, sorry, partial derivative of this with respect to Pi?
1 by 4 by
So it is 1 by sigma I square plus Pi plus lambda minus lambda 2I. This should be,
also
so this lambda is, okay, if you want, let me call this lambda 1. So lambda 2 is a vector, whereas lambda 1 is just a scalar. Pi plus lambda 1 minus lambda 2I should be equal to 0. And of course, we have the non-negativity constraints that lambda 1 should be greater than or equal to 0. Lambda 2I should be greater than or equal to 0 for all I. Okay.
Sir.
Yeah.
So log is concave, right?
Yes.
So we not need to make it convex negative. Or negative.
We're maximizing the. Okay, let's look at the other KKT conditions. So, well, I have these. So lambda 1 should be greater than or equal to 0. Lambda 2I should be greater than or equal to 0 for all I. I have Pi should be greater than or equal to 0 for all I. Summation j equal to 1 to m. Pj should be less than or equal to P. Right. What else do I have? Yeah. We could, but fine. That's not. Ultimately, we'll see that it won't matter. It will be satisfied with this quality. What are the other things that we have? So lambda 1 summation j equal to 1 to m pj minus p should be equal to 0, and lambda 2I pi should be equal to 0. Okay, so we know that lambda 1 should be greater than or equal to 0, and lambda 1 is basically equal to lambda 2i minus 1 by sigma I square plus pi. Correct. So effectively what we are saying is that lambda 2i minus 1 by sigma I square by plus pi should be greater than or equal to 0. Right? So from 1 and 2, lambda 2i minus 1 by sigma I square plus pi should be greater than or equal to 0. Okay. And we know that either lambda 2i should be equal to 0 or pi should be equal to 0. Or pi should be equal to 0. So if I sort of rearrange things over here, so this would be pi 1 over pi plus sigma I square should be greater than or equal to lambda 2i. Sorry, less than lambda 2i, or in other words 1 by lambda 2i should be less than or equal to pi plus sigma I square, or pi should be greater than or equal to 1 by lambda 2i plus, oh, I'm sorry, I think okay, so let me do this the following way. I'd say that lambda 2i, to solve this differently, lambda 2i equal to lambda 1 minus this. So lambda 1 plus 1 by sigma I square plus p. Right? So this tells me that lambda 1 plus 1 by sigma I square plus pi is greater than or equal to 0, or 1 by pi plus sigma I square is less than or equal to uh, minus lambda 1. Minus lambda. Sorry, yeah, how much? So this is greater than or equal to 0. So this is greater than or equal to, this is
Reciprocal.
1 over lambda 1 square pi. Did I make a mistake? Let's, let's maybe continue in the next class.